G be an abelian group, and let H is equal to set of all x in G such that order of x is odd. Then we have to prove that H is a subgroup of G. Okay, so when will H be a subgroup of G? First condition is H must be closed. That is, given any x and y in H, then we need that xy must also be there in H. Okay, then second condition is identity element must be there in H, and the third condition is given any x in H, we must have that x inverse is also given any x in H, we need x inverse also to be there in H. Okay, so these are the things that we must verify. Okay, so here consider identity element. What is order of identity element? It is 1, okay, which is odd. So this is definitely satisfied. Identity element is definitely there in H. Okay, all right. Now let's check the first one. Okay, now consider x and y in H. That means order of x is equal to m, it is odd. Okay, and order of y is equal to n, and that also must be odd. Okay, we have to show that xy is there in H. That is, we have to show order of xy is odd. Okay, that is our idea. All right, now what will we do? Consider mn. Okay, consider xy to the power mn. All right, now what is this? This is nothing but xy times xy, etc. times xy. How many times? Mn times. Okay, now consider we will use associativity, and here what we will do is in the first two pair we will okay, we will keep it as x times yx times y. Okay, then rest of the pairs we will keep it as xy itself. Okay, now this is by associativity. Okay, then we will use the abelianness of group. This is where the abelianness comes in. So this way we can write this as x times xy times y. Okay, times xy, etc. up to xy. Okay, now here again we will use the associativity, and we will have x square, y square, then xy, etc. up to xy. Now continuing like this, we will have that this is equal to x power m times x power mn times y power mn. Note that in general for any group ab whole power n is not equal to a power n b power n. This is not true in general. Okay, in later on in one of the videos we will give an example where ab power n is not equal to a power n into b power n. Okay, now here in abelian groups it is true. Okay, in abelian groups it is true. That much only we are guaranteed of. Okay, so here G being abelian is very important. Okay, now this what did we have here now? Xy whole power mn. This is actually equal to x power mn times y power mn. This I can write this as x power m the whole power n and y power n the whole power m, right? Then this is actually equal to identity time, power n, which is again identity, times identity, which is nothing but identity, right? So xy power mn is identity. Now we are going to use a result. Okay, maybe I'll prove this in one of the later videos, that if a is an element in the group G, and if a power say p is equal to identity, then order of a will divide p. Okay, this maybe I will prove it in one of the later videos. Okay, now so here we will have that order of xy must divide mn. Now mn is odd, so uh, xy order of xy must also be odd. Why? Suppose xy is even. Sorry, not xy, order of xy. Suppose order of xy is even, then what will happen? Then we'll have that order of xy is equal to some 2 times, say for example it is 2 times q. Okay, for some q, where q is in natural numbers. Okay, then we know that order of xy divides mn, so mn must be equal to some multiple of this order of xy. So it is equal to, say for example, r times order of xy. So it is equal to r times 2 into q, which is equal to 2 times rq, right? So that will mean that mn is even. So that is a contradiction. Mn is even, Mn is even, which is a contradiction. Why? Because m is odd, n is odd, and product of odd is again odd, right? So you can definitely prove that. It's a very easy thing. You can take m to be equal to, say for example, 2a plus 1, and then n to be equal to some 2b plus 1. Then if we are taking mn, then you will get this as 2a multiplied by 2b, which is 2 times 2ab. Okay, then plus 2a plus 2b plus 1. So from this we can take 2 common outside and we'll get 2ab plus a plus b plus 1. So mn has to be odd, right? So this is one thing. So what we were saying, xy is sorry, mn is odd, so order of xy must also be odd. Okay, so order of xy is odd implies that xy is in h. Okay, so if x is in h and y is in h, then xy also must be there in h. Now, what about the third one? For the third one, again, I am going to use a result that if x is an element in h, or if x is an element in the group G, then order of x and order of x inverse must be the same. Okay, I'll again prove that in one of the later videos maybe. Okay, so order of x and order of x inverse are the same. So what will happen? So here x is in h, so order of x is odd. Okay, and order of x inverse is the same number, so order of x inverse is equal to order of x, which is again odd. So order of x inverse is odd, so x inverse must be there in h. Okay, so let me just write that down. So here we'll be using a result that if x is in G, any group G, okay, then order of x is equal to order of x inverse. Okay, now let x be in H. Then this implies that order of x is odd. Okay, now this implies that order of x inverse is odd. This implies that x inverse must be there in H. Okay, so all the conditions are satisfied and hence H is a subgroup, okay, of G. So I have to prove these two results. It will be done in one of the later videos.